Part 3, lecture part 4, where we're going to be talking about the naming and writing of molecular compounds. In the last video, we focused on talking about ionic compounds, and just to remind you, ionic compounds typically have a metal and non-metal, or there'll be a polyatomic ion in there. But now what happens if we are not talking about ionic compounds? To remind you, and again, I wrote some notes here on the side that you could write along when we're doing it. To remind you, a molecular compound is one that contains two nonmetals. And to remind you again, if you look at a periodic table, and I'm going to scroll up just to look at a periodic table, our nonmetals tend to be on the right-hand side of the periodic table here. They can be found in ionic compounds, but they have to be bound to a metal. But what happens if I have two nonmetals, like N and O or N and S, forming a compound? So let's talk about that here. So, in contrast, the formula for a molecular compound cannot be readily determined. They could bond and form in many different ways. Like, for example, carbon could bond to oxygen once or twice. Or hydrogen could bond to oxygen twice or 2 times. These are going to get a different set of rules. Why? Well, if we were to use the ionic rules, like name the left cation metal first and then the nonmetal, all of these compounds would be named the exact same, and that would be a problem. Think about why that would be a problem. Why would that be a problem? Because how can we tell? How can we tell what's what? And that could be dangerous in a lab if we don't know the name and identity of compounds. Every substance has to have its own unique name. So here's how we name, and then eventually we'll write formulas for molecular compounds. Since these molecular compounds can combine in multiple ratios, we're going to use something called Greek prefixes, right? And so the way that they would name it, we would have a Greek prefix, then the name of the first element, and then another Greek prefix, and then the base name of the second element ending in IDE. So it still has that same IDE ending for the second element, but now we're adding in this idea of Greek prefixes. Okay? The only note about the first element is we don't use mono on the first element. So mono is if I have one of an element, di is if I have 2, tri 3, tetra 4, penta 5, octa 8, hepta 7, hexa 6, and so on and so forth. So here's just a couple quick examples here. If there's only one atom of the first element, like I said, the prefix mono is normally omitted. It's not usually used, so I wrote that there. So let's look at how I named NO2 and N2O. NO2, there's one nitrogen. I could say mononitrogen, but it's not typical, so I would just say nitrogen. That means I only have one. And then dioxide. Di means I have 2 oxygens, NO2. And then look at the next one. Now I have 2 nitrogens. So now I have dinitrogen, and then I do have to add the mono for that second element, monoxide or monooxide. And just to make a little note there, typically monooxide will just become monoxide. Kind of like in Spanish or other languages, a lot of languages don't like to use like a double vowel sound, except for English, right? A lot of languages don't like to use a double vowel sound, so they kind of just drop one of them. So monooxide just becomes monoxide. You'll see the same with like tetraoxide. That will become tetroxide. Anything that's like AO, we just drop the A and we leave the O. So if it was like octaoxide, that would be octoxide. Just a little note there. All right, so in general, I look at a formula. How many of each are in the compound for 2 nonmetals? This is for molecular compounds. How many of each? I use Greek prefixes. I have a bunch more examples. We'll do a bunch together. I already have one done here, PCl5. There's 1 phosphorus, so I say phosphorus. There are 5 chlorines, so I'd say penta for the 5, and then I end with chloride. I'll do the other ones. I'll do them in black so you could see. Ni3, that would just be nitrogen since there's only 1 nitrogen. And then the Greek prefix for 3 is tri, so it'd be triiodide. Okay? And no, the I's don't drop there. It's only if you have 2 different vowels there. We're not going to be big on spelling here. As long as you know to use tri, we're good to go. Then let's do the next one. I did this kind of on purpose so you get used to more prefixes. P4S10. P4. Oops, I have 4 phosphoruses. So 4 is tetra. So it'd be tetraphosphorus. And then I have S10, 10 sulfurs. 10 is decoxide. See, the AO drops to just O. N2O5 would be dinitrogen. Again, I got dipentoxide. Pent for 5 oxygen. Now, we're not going to have to worry about charges and figuring out any type of math with writing the formulas for molecular compounds. You're going to love this. You just use the Greek prefixes to write the formula. Look at disulfur pentoxide. Disulfur means I have 2 sulfurs. Pentoxide means I have 5 oxygens. S2O5, done. Phosphorus tribromide. Phosphorus, I have no prefixes, so I assume just 1. So phosphorus tribromide. I have 3 bromines. Done. Chlorine trinitride. 1 chlorine. I don't have any prefixes, so I just assume it's 1. Trinitride. N3. Done. And so I'd like you to submit with this work exercises 11 and 12. I did do 2 answers here. For 11, you're going to name each compound. For 12, you're going to write them. And I did 2 answers. I did SO2. SO2 would just be sulfur dioxide. And then for number 12, I did the formula for carbon tetrabromide. It would be CBr4. Tetra means 4. I'm going to end this lecture with just a quick little thing here. This is not going to be big in our summer work, but I wanted to introduce it briefly here. Please read through this. You're not going to have any examples, but we're going to see it again in the winter, in December. We have something known as acids. You've heard of and you've probably experienced acids. Like if you ever have a pop or a Coke or a Pepsi, Diet Pepsi, anything like that, you'll feel that little burning. That's carbonic acid when you drink. When you drink and you feel that little burning, that's carbonic acid. Or like vinegar. Vinegar that sometimes is found in salads or other drinks or terrible drinks or foods. Vinegar is made of acetic acid, HC2H3O2. Acids take the form of HA. They have an H in the front. It stands for this H+. We call that a proton. And then A is some anion. A stands for some anion that it's next to. So I have just 2 examples. HCl, this is hydrochloric acid. We have H, and then Cl would be the Cl-. We have HC2H3O2. We have H, and then the C2H3O2 would be our kind of counter ion anion. You just have to be able to recognize something as an acid. Like I have more examples here, HBr, HNO3, H2SO4. If something typically has an H in the front, that will typically be known as an acid. For our summer work, I just want you to be able to recognize them, see them, and we'll work with them in other calculations, but it's not going to be big. You are not going to have to worry about naming them for AP Chemistry. It's just very important to recognize them. And then on the bottom of our page 12 here, there is a nice little summary for naming flowchart. Again, you're not going to have to worry about this, not for AP. You're not going to have to know how to name acids for AP. You're not going to have to sit there and just like name an acid. You have to recognize it, definitely, but you're not going to have to sit there and name it. Ionic and molecular for our summer work, I want you to have that kind of base knowledge on how to name and write formulas for ionic and molecular. Remember, ionic, metal and nonmetal, or polyatomic ion. That's found in there. Molecular would be 2 nonmetals only. And here's our nice little flow chart for how I name and write their formulas. Alrighty, that is the end of our Part 4 here. Again, if you have any questions or concerns, if you're struggling to name and write the formulas for molecular compounds, feel free to reach out, remind, or email.